We are going to finish up here chapter 10. So we've been talking about energy in this chapter. More specifically, we were talking a lot about sort of specific heat last time. And remember, with specific heat, we have the equation that we use for Q is equal to ms delta T. A reminder that in terms of Q, that is the heat or energy, and that usually has units of joules or calories. So once again, that is the one that has really just the one unit, the joule or the calorie. And as we talked about the relationship between those two units, 4.184 joules is a calorie. So again, that's sort of our conversion factor. M is the mass, which is typically in units of grams. S is the specific heat capacity, which is the one that actually has the three different units. It is joules per gram per degree Celsius, or calories per gram per degree Celsius. And we did talk about, and a lot of times when you're doing specific heat type problems, we do use the specific heat of liquid water a lot. And that is either 4.184 joules per gram per degree Celsius or 1 calorie per gram per degree Celsius. So remember that those are two numbers that you should know. We use it a lot when we do these type of experiments. And a lot of times we do use the joule sort of version of it most of the time. The really important thing as well in this calculation is also the delta T that we talked about, which should be our final minus our initial temperature. And it is one of the few sort of chemistry things here that we do leave in degrees Celsius, because usually our specific heat capacity is in degrees Celsius. So one of the rare times that we do that. As we talked about, it is really that change in temperature value that's going to determine whether or not this process is going to kind of be exothermic or endothermic overall, because that's really the one that's going to give you a negative number. You should never get a negative number for mass. You should never get really a negative number for specific heat capacity. So as you do your post-lab questions today, you should not get a negative number for mass or specific heat capacity. They should always be positive numbers. But again, that change in temperature will allow us to figure out whether or not Q is going to be negative, which means it will be exothermic, or again, Q, which could be a positive number, which means it will be endothermic. As you'll do today in lab, as we talked about last time, we'll talk a little bit more about today. You can really simply do this type of experiment with coffee cups, basically. And for the most part, you've got a thermometer going on there. For the most part, most solutions, even if you weren't doing like we're doing today, where you put the solid into a liquid here. If you mix two solutions together, most solutions are aqueous in nature. Stands for aqueous. And that usually means it's really like water. So oftentimes, even if we're mixing different reagents together, they're of aqueous solutions and water-based, we could very simply do this reaction in a coffee cup and follow the change in temperature and relate it back to water and figure out how much heat is being released or how much heat is being absorbed in a particular reaction. And when we do this at constant pressure, when we calculate Q, it actually will equal the delta H, or the enthalpy of a reaction in this situation, and makes it a super convenient sort of way of figuring out the enthalpy for a particular reaction. Usually in 1A, you do an experiment like that where you mix multiple things in coffee cups like you're going to do today. Today, you're basically just following the heat transfer of a solid, obviously, to water. But you could do actual chemical reactions in this sort of setup, very much like what you're doing today, to follow the heat and also follow the enthalpy that's going to happen in that particular reaction. Any questions on any of that stuff we talked about last time? Okay, then let us continue on here, I think. So we'll talk a little bit about energy and nutrition. I think we touched upon it kind of earlier. There is sort of another unit of energy that's sometimes used, but it's really more a nutritional sort of value, and that is a capital calorie there with a capital C. That is a nutritional calorie, and a reminder that sort of one of the capital calories is actually 1,000 of the little calories and 1 kilocalorie. So although we don't use it too much here in chemistry, when you do see that sort of capital calorie, it is a nutritional calorie, and it is 1,000 of that little guys. A calorimeter is kind of like the apparatus we're using today in lab, and in general, it is a sort of system or apparatus that you can use to really measure the amount of heat and energy is given off. And one way you can do that is through the use of like a calorimeter such as this, sometimes referred to as a bomb calorimeter, because basically you set the thing on fire there. So it's sort of a nice insulated container, and we have water inside. We have sort of our reaction chamber where it's filled with oxygen and some ignition wires. Clearly, we can ignite the oxygen that way. We have our food sample, like our cookie, and we basically set it on fire. And as it's burning and cooking, basically it's going to give off all the heat and energy, which will go right into the water, right? So since this is a nice insulated container, kind of like our coffee cups, which works kind of the same way, we're not going to lose anything to the surroundings. So 100% of everything that the water is picking up would come from obviously the food burning. We can use our change in temperature of the water and really our very simple specific heat equation, and we could figure out how much heat and energy that the water basically gained in that case. You could do it in joules, or you could do it in little calories, and you can convert those little calories into kilocalories, which would then give you basically the nutritional calories that you get. Kind of like what you find on your package of food, right? It says, hey, this is 200 calories per serving and stuff like that. How they actually do get sort of those values that you see on those nutritional labels is, for the most part, most foods broken up into 3 sort of categories: carbohydrates, fats, and proteins. And each one has a caloric value associated with it. So something like carbs and protein are 4 kilocalories per gram. Something like fat is 9 kilocalories per gram. Once again, a kilocalorie is basically a nutritional calorie. So if you look on like a nutrition label on your food and stuff like that, you will see, it will say, hey, there's 30 grams of protein and 30 grams of carbs, or 100 grams of fat, or whatever it may be there, whatever you're eating. And they basically do this sort of simple calculation to get you that number up on top of how many total calories there are. And you basically just take the grams of each of those, and that gives you the kilocalories for each of those things. And then you add up those 3 categories together. And like I said, that's essentially how they get the overall calories. And in my experience, they usually like to round down on the calorie overall count there. But that's basically how they come to those numbers. More like what we're going to do today, and really sort of a simpler sort of setup, is, like I said, you can do constant pressure calorimetry, which is usually what happens because the pressure of the room doing it in doesn't really change all that much. And we could really use it to measure a wide variety of different reactions, as we talked about. Since most solutions are water-based, pretty much can just do the calculation for water and relate it to the reaction that's going on there. And this is pretty much your setup for the experiment today that you're going to do. You'll have your water inside your coffee cups here. You want to make sure you get the mass of the water and the initial temperature of the water. You will have your metal up here in the boiling water. You want to make sure you get the mass of the metal and the temperature of the boiling water before you transfer. You will then dump it into here. Temperature should go up in this case. Now, obviously, in the case of the experiment you're doing today, you should see the water gain all that energy from the metal, right? Because it's much hotter, right? So it'll be endothermic for your water. You should end up with a positive Q value. The amount of energy that was released by the metal should be equal to the amount of energy that was absorbed by the water, but the sign should be different for the metal, right? Because the metal is giving off the energy, should be exothermic, which means your value for Q for the metal should be the same number, but negative when you calculate it in that particular case. Again, using these coffee cups keeps it really nicely insulated that we, for the most part, aren't losing any heat and energy to sort of the surroundings. Again, this sort of simple setup, like I mentioned, is a way that you could relate it to the change in enthalpy for a reaction by just basically following that temperature change. Any questions on that there? All right, so let's take a look at sort of a nutritional calorie sort of calculation here and what we would go through. Maybe too far. Good luck. All right, so if we did have, say, 28-gram serving of some cereal and a little bit of milk, and it gave us a total of 22 grams of carbs, 7 grams of fat, and 10 grams of protein. We want to know how many kilocalories would we obtain from that meal. So basically, this is the total amount of carbs for our meal. This is the caloric value for carbohydrates. This is the total amount of fat from our meal, and our caloric value for our fat and for our protein and our caloric value. These are all basically the calories being associated with each of those things. When we add them together, that's basically 191 nutritional calories, which is the same thing as a kilocalorie. And since we had 2 servings, we would multiply by 2. And from this breakfast here, we would end up with about 382 calories, nutritional calories, or kilocalories that we ate. So obviously, you could figure out things like, if you swam for 2 hours, how much of that meal you would have burnt off and that type of stuff. If you knew how many kilocalories of you were burning per lap or whatever you may be doing there of swimming. Any questions on that calculation there? Okay. So really the last thing we're going to kind of talk about here in this chapter, or one of the last things, is the idea of equations and the delta H values. These are sometimes referred to as thermochemical equations because they're equations that has a delta H value or energy value associated with it. As I mentioned, I think last time, a very common, like we see in the very top equation there, that's oftentimes how things are sort of displayed to you in terms of energy and equations. You're given an equation, and then essentially you have the delta H value given to you next to it. So that is basically solid water going to liquid water. That is basically our ice cube melting is basically what's happening there. In order to do that process, it takes 6.01 kilojoules. Melting of ice should be a endothermic process. So that is why we see the 6.01 is a positive number, which tells us overall energy needs to be put in to do that. The opposite, though, process where we would maybe take liquid water and throw it in the freezer to get our ice cubes back is the second equation. And really the only difference between the first equation and the second equation is we reversed it, right? So instead of starting at solid and going to liquid, we're starting at liquid and going to solid. So it's basically the reverse of the equation there. What happens in terms of the energy to do that is it is the exact same number, as we can see, is 6.01 in each case. The difference is, though, when we go from liquid to solid, in this case, it is exothermic, which means the number should be a negative number. So we have our negative number. By the way, that's the process. And as we talked about, I think at a earlier time, that occurs at the same temperature or different temperatures. That actually occurs at the exact same temperature. Remember, at exactly, for example, water at 0 degrees Celsius, you have basically kind of liquid water and ice happening at the same time. Exactly at 0 degrees Celsius is where the substance changes phases. This actually has a special name, as we'll see in a later chapter. This is what is known as the heat of fusion. And the heat of fusion is the energy required basically to do this process, to do nothing more than take a substance from the solid state to the liquid state, are going the other way. Take a substance from the liquid state back to the solid. So diffusion for water is 6.01 to do that. And it's this number regardless of which way you're going, but the sign again would change depending on which way you are basically doing. So the take-home message here of this type of situation is there will be situations where you will have an equation that has a delta H value associated with it, and specifically Hess's law, which we're going to talk about next. You may need to reverse a reaction. So whenever you reverse a reaction, what happens to the delta H is it changes sign. So the number stays the same, but the sign changes. So if it originally was a positive number and you reverse it, for the reverse reaction is a negative number and vice versa. When you do see a delta H value, it is specific for exactly how the equation is written. So if you do something equation, the delta H value changes accordingly. And the one major thing that you could do is reverse it and you would change the sign. Another very common sort of process that sort of occurs when we use these type of equations and delta H values is maybe we don't need one of the water, but maybe we need two of the water. So there are times where you might need to take an equation like the top equation and actually multiply the entire equation by a common number. And if you find yourself in the need of multiplying an equation by a common number, what you would do for the delta H is also multiply it by the same number. So if you have to multiply an equation by a common number, the way you adjust the delta H value is to multiply the delta H value by that common number. The last thing that you could do is basically divide by a common number. So let's just say, for example, we started with this equation and we actually just needed one of everything. We would have to go through and divide everybody by 2. And when we divide everybody by 2, we would get to the top equation. And if we take 12 divided by 2, we are back to our 6.01 in this case, with a little bit of rounding and stuff like that. So those are 3 very common things that you have to do when you're doing Hess's law type problems, which we're going to talk about next. You sometimes need to reverse a reaction, which means you need to change the sign of the delta H. You sometimes need to multiply the entire equation by a common number, which means you should multiply the delta H by the common number. And lastly, you may have to divide an equation by a common number. You would then divide the delta H by the common number. Clearly, if you didn't have to do anything to any of the equation, you just take the delta H as it stands, right? So sometimes you may not have to do any of those things. You would just take the equation like it is. Any questions on that there? Yeah. Yeah, so technically that number that we see up there is technically kilojoules per mole. And you would, yeah, so if you had, like you said, basically 1 mole of water, which would be 18.02 grams, you basically would, you would probably, if you were using that number, which would be kilojoules per mole, you would leave it as like 1 mole and you would times it. So that's why it would be technically 6.01. But if you had 2 moles, you would then obviously times it by 2, which is essentially what this is doing, right? In this case, this number in front could be thought of as moles. So in the top one, there's 1 mole gives us 6.01. But if we double the moles of the water, we get double the energy. And opposite, if you go the opposite way around, if you started with 2 moles and you don't get down energy. Okay, so let's talk a little bit about Hess's law and the idea behind Hess's law. The idea behind Hess's law is sort of the idea that we talked about earlier, which is the idea of state functions, which means if you remember, there was those sort of mountain climbers, and one guy went directly up the hill, and one guy took like the scenic route up the hill. And in chemistry, not all reactions basically take place in one step, as we might have talked about. It could be multiple steps to get you there. So once again, if you had an overall reaction of like A plus B goes to E plus F, this may occur in a multiple step process where maybe we got a couple of guys going here. And for each of these steps along the way, there would be some energy associated with each of those. And if we add these steps together, which is very common, what you do in sort of a Hess's Law situation, you think of the arrow as like an equal sign. So anything on opposite sides of the arrow will cancel each other out or reduce down. So since C is on the left and C is on the right, they will cancel. D is on the left and D is on the right, so they will cancel. And then anything on the left-hand side of the arrow stays there. Anything on the right-hand side of the arrow also stays there. And that would give us the overall reaction that we are looking for in this case. And if we wanted the delta H for this reaction, we would basically just add up the delta H values for each of the steps along the way. And that's what we see here. If we look at the guide to the left, this is basically some water being made. It's a result of a sort of two-step process here. H2 plus a half of O2 makes H2O gas, has a certain amount of energy associated with that step. Water, liquid state, also has a certain amount of energy. That's also known as the heat of vaporization, this process. That's 44 kilojoules. Adding together, the waters will cancel in the gas state, leaving us the overall reaction. And in this particular case, we would just add both of those values together. The minus 241 and the minus 44 gives us overall for this process the delta H reaction of the reaction as minus 286, basically. This is a exothermic process, as it is overall negative, right, to delta H value here. So overall, this is going to be releasing some energy as this process occurs. Any questions on up there? So in this particular case, we really didn't have to kind of adjust any of the equations. They were really set up exactly the way we sort of wanted them. But there are going to be situations where you will have to sort of adjust the equations and keep track of what you're doing. So for example, let's say we did have something like 2E plus 2F go to A plus B, and we wanted to figure out the delta H of this reaction. And we wanted to basically do this using two equations. So we'll do A plus B goes to 2C plus 2D. We'll go delta H here is going to be minus 200 kilojoules. And then C plus D goes to E plus F. We'll go delta H for this guy, positive, say 50 kilojoules in this case. So what we're looking to do is build the top equation, use the other two equations to figure out the H of the top equation. So once you take a second, again, in this case, you may have to move some things around. You may have to manipulate some equations. You want to keep track of the delta H values and what you need to do to them. And then you want to add everything together to get that reaction. I'll do it as well since I just made it up and I'm hoping for the best. Let's see here. So take a minute or two to see what you come up with first. So again, the goal here is to use these two equations to build that equation there. And again, may require you to reverse a reaction, multiply by a number, divide by a number, maybe not do anything. Okay, let's take a look, see how you're doing. So here's sort of the approach you should do when you have to do a Hess's Law problem like this. You usually will have multiple equations given to you, as you can see there on the bottom. Maybe two, maybe three, maybe four, maybe a lot of different equations sort of given to you. The goal is a really simple approach is probably the best way to do it. And the way I do it is personally, I look at the equation I am trying to find, and I simply just make sure two things are there. are they on the right side, right? I just want to get everybody to the correct side of the arrow. And I want to make sure that I have the right amount of everybody on the correct side of the arrow. And that's really a good way to sort of approach it. So if I was looking at this, I would see I definitely have E over here on the left-hand side. The only equation that has E in it is actually the bottom equation, right? And it's on the right-hand side, which means it's on the incorrect side for what I need. First is going to tell me I got to take the bottom equation and actually reverse it to get the E to the correct side. In addition to having E on the left-hand side, I need how many of them? I need 2, which I only have 1 in the bottom one. So that tells me 2 things. I need to actually reverse the bottom equation, and I need to multiply it by 2. So that is the first thing I'm going to do, is I'm going to take the bottom equation and I'm going to reverse it. And when I reverse the bottom equation, what happens to the delta H value? It now becomes negative 50 in this case. So this would now become negative 50. I also need to multiply it by 2, which means technically I'm going to take this entire equation and multiply it by 2, which would give me 2E, 2F, 2C, and 2D. Because I multiplied the equation by 2, the delta H then needs to also be multiplied by 2 to give me the correct value, which means I'll try it without a calculator, but I'm going to go with minus 100 kilojoules here. Hey, you know, math and chemistry was my bad subject, so I'm trying. So that gives me the correct delta H value for that equation that has now been sort of manipulated correctly to what I need. By just doing that bottom equation, it also took care of my problem here for F, right? So I got that all situated out. Then I'm just going to continue on like normal here to the other side. I see that I need A, and it's on the right-hand side of the arrow. The equation that has A in it is the top one, but once again here, it is on the incorrect side. It's on the left-hand side. I need it on the right-hand side. So once again, that's going to tell me I need to take the top equation and also reverse it, right? Now I only need 1A, and there is 1A in that, which means I don't need to multiply by anything. I just simply need to take that top one and flip it around. So I'm going to take the top equation and reflip it or reverse it. So that gives me 2C plus 2D gives me A plus B. And now because what I did with the first equation there was simply just reverse it, the delta H value for that first equation is now going to also change its sign, and it's going to go from negative 200 to now positive 200 kilojoules. Any questions on that there? I am clearly out of equation, so hopefully I should have done it right at this point. I would hope at this point. And we will make sure by adding these together. So we're going to simply add these 2 equations together. Once again, anything that's on opposite sides of the arrow will cancel. And it doesn't necessarily always has to completely cancel, but it could reduce down. So you could think of the arrow like an equal sign, like you're subtracting from one side to the next, like in math. So in this case, I have 2C on the left, which has 2C on the right of the arrow. So those guys would completely cancel each other out. The 2D on the left will also completely cancel out the 2D on the right. At this point, there's nothing else that's going to cancel. So whatever is left over at this point, everybody that's on the left-hand side of the arrow stays on the left-hand side. Everybody on the right-hand side of the arrow will stay on the right-hand side of the arrow. And that would give me my 2E plus my 2F goes to A plus B. So first off, I can see by adding those equations and moving them around, I hit the equation I'm looking for, which is good. So clearly, if you get to this point and that equation doesn't match, something went wrong, obviously. So you should hit the matching equation there. Now I can find the delta H of this reaction by simply adding all of my adjusted delta H values for everything I did. So that would be technically this number, and this number here would be added together to give me the delta H value for this, which would be minus 100 kilojoules plus a 200 kilojoules. I'm going to go again without the calculator and try 100 kilojoules and hope for the best in this case. And that would tell me that this reaction overall will yield 100 kilojoules of energy. And this will also tell us if this reaction is exothermic or endothermic. It is endothermic, as we ended up with a positive value. So really, Hess's law, people always freak out about Hess's law. There's like lots of equations and like, what am I supposed to do with these things? So it's really like a puzzle. You just want to take the individual equations, move them around. And again, in some cases, you may not even have to move an equation. Just leave it the way it is. But you just want to get everybody, those two things, everybody to the correct side of the arrow and the right amount. And usually what will happen is as you start moving and sort of correcting one thing, it will kind of fix everybody else along the way, and everything will sort of fall into place. Any questions on that there? The Hess's law. So Hess's law is the idea, kind of like the idea of state functions. So state functions basically means, and enthalpy is a factor of the state function, basically means it doesn't matter how you get there. The only two really important things are kind of where you started and where you ended up. Now, if that took you like 400 steps to get there, it doesn't really matter. Or if you were able to do it sort of in a 2-step process or a 1-step process, in terms of the overall energy, like the delta H in this case, the only difference is like where you started and where you ended. So although it took us 2 steps to do this, where we started was really here and where we ended was really here. And really, ultimately, it is the difference in energy between here and here that results in the delta H value that we see. And that's why we could use all these individual sort of energy steps and add them together to get us there. So that's sort of the idea behind Hess's law. Is kind of the idea as well of like, you know, if you took, and we'll talk about it probably in a later chapter, but if you took like a nice piece of ice and you heated it, it goes through many different changes until it gets to like gas, right? So you have like, say, if you had ice at like -5 degrees, it's got to go from like -5 degrees to 0 degrees in ice, and then actually has to do a phase change. It goes from 0 degrees ice to 0 degrees water. Then it's got to go from liquid water 0 degrees to 100 degrees liquid water. Then it's got to go from liquid water at 100 degrees to basically steam at 100 degrees. And then maybe you stopped at 105 degrees. So then it's got to go from 100 to 105. That whole process, right? There's a lot of individual steps to get us there. But ultimately where we're ending is at gas at 105 degrees, and we started at -5 degrees. The amount of energy to get us there is simply the addition of all those steps along the way. And that's sort of the idea of Hess's law, is basically that idea that you're just keeping track of all the energy on each of the pathway to get you there. And overall, if you do that, it'll give you basically where you started, where you ended, the difference in energy. Other questions? Yeah. So let's take a look here. Actually, let's do a different one here. Let's do what is the delta H for let's do 4 CO2 to 4 carbon and 4 of the oxygen. All right. So we're looking for the delta H of this reaction using these two equations down here. What's that? Of the states. You can, if you want. Sometimes it gets a little bit crowded as you're doing these things and moving around. You could leave them off and kind of put them in at the end if you want. But you just got to remember, sometimes you may have the same sort of substance in different phases. So sometimes it's kind of important to keep it. So I think the previous example, we had water that was in the gas phase, and we also had water in the liquid phase. So you need to keep track of that, because you may be able to cancel something out and not cancel something out. Because if you had water in the gas phase and say water in the liquid phase, they would not cancel. So I would say in a lot of cases, it's probably safe you can get rid of the little parentheses, but if you have multiples of the same substance in different states, you might want to keep them so you know if they will cancel or not cancel. Okay, so once again here, we're basically trying to build from these two equations the top equation. So just keeping it simple, I'm going to look for my CO2, which is on the left-hand side. Here's my CO2, which is on the right-hand side. So once again, here we are going to have to reverse this guy. We also need 4 of them, so we're going to also have to multiply it by 4. So we'll do that first. Multiplying this guy by 4, which would also multiply our delta H by 4, will give us 4 of the CO2 goes to 4 of the CO plus 2O2 when we multiply the 4. Once again, our delta H value will now become positive 283 times 4, positive because we reversed the reaction, and 4 because we multiplied by 4, which would give us 283 times 4, about 1132 in terms of energy there. Questions on that so far? Next, I'm going to roll to the other side where I see carbon there on the right-hand side. Once again, carbon is on the left-hand side here. So we're going to reverse it, and we also need a 4 of that one as well. So we're going to multiply the top one by 4 as well. So reversing it will give us 4 of the CO and 4 of the carbon plus 2 of the O2 there. And that will get us a delta H that we also will become a positive 110 times 4. Again, positive because we reversed it, and 4 because we multiplied by 4, which will give us our 440 in this case. All right, so if I did this right, I'm hoping this will cancel. And I think that will be it. That will leave us 4 CO2 on the left, right-hand side of the arrow, 4 carbons, and 2 and 2 gives us 4 of the oxygens. Delta H would be, once again, adding our numbers here together that we sort of manipulated, and we will end up with like a 1572 in this case. Which once again is a positive number and a endothermic process. Any questions on that there? It will, so to answer your question, I think to answer your question is this. What will typically happen is some of the other stuff will just kind of fall into place once you kind of get some of the other ones. Yeah, a lot of times it's good to do it may not always work out nice and pretty like this, because might have maybe the O2 first written. So in a case where maybe you have something like the O2 where you see it in both of the equations, you probably want to leave that to the end and just kind of focus on the things in the overall equation where there's just kind of like one of them and they're just found one time in each of the equations. And then leave those guys that are maybe multiply found in multiple equations, and that usually will allow it to all kind of fall into place in most cases. Yeah. Is that your question, or yeah? Other questions on that? Yeah. Let's try one more here. All right, we are shooting for this equation here based on those 3 equations. So in this case, we have 3 different equations to work with. Just a couple minutes, see what you come up with here. Look, so again, in this case, we have 3 equations. It doesn't really matter. We're just going to take the same sort of approach. I'm going to start here with the carbon, and the only equation that really has the carbon here is the first one. I need the carbon at the end to be on the left, and it is on the left over there. I also need 1 of the carbon, and I need 1 that's up there. So really, in this case, I don't actually have to do anything to the very first one, which does happen. You might not have to do anything to that first equation. So I'm just going to recopy the first equation. Once again, here, I didn't need to do anything to it. And because I didn't do anything to it, its delta H value will remain the same at minus 393.5 kilojoules. I'm then going to move to my next one, which is sulfur here. and I do need sulfur on the left, and the equation that has sulfur is the second one, and it is on the left, but again, in the end, I need two of them, and I only have one in that equation. So I am going to need to multiply that equation by 2, which means I will also multiply my delta H value by 2. When we multiply the equation by 2, we are multiplying everybody that is in that equation, not just the first guy. So we would multiply all the way across everybody in that equation and give them a 2 in this case. Delta H will remain the same at minus 296.1, but I do need to multiply it by 2 because I multiplied everything else by 2 to give me the correct amount of kilojoules. And that would be, just to get the number at this point, looks like maybe minus 592.2 kilojoules. Any questions so far? Lastly, here we have the CS2 that's on the right-hand side. I have my CS2 here on the left-hand side, so I'm going to need to reverse the last equation. I don't need to multiply in this case because the CS2 is 1 in each of them, so that's all good. So we're just going to reverse the very last equation, and when I do that, I'll end up with CO2 on the left, 2 of the SO2 on the left, and reversing it will now put my CS2 on the right and my 3 oxygens there on the right. Because all I did to this last equation was reverse it, the sign is the only thing that's going to change here. So it's going to go from negative down to positive 1072 kilojoules. Any questions on that? At this point, I am clearly out of equations, so I'm hoping I did everything right. We're going to do some crossing out. So on the left-hand side, we have CO2. On the right-hand side, we have CO2, so those guys will cancel. Left-hand side, we got a couple of SO2s, and a couple of those guys will cancel. On the left-hand side, that is 1 O2, right? And then if I were to add it to the guy below it, which is also on the left-hand side, that would give me 3 O2s, which 1 and 2 make 3, would cancel out the 3 O2s that I have on the right-hand side. So once again, that's how those 3 would cancel out. At that point, I don't have anything else to cancel, so everybody on the left stays on the left. So that would be my carbon plus my couple of sulfurs going to my CS2 liquid. Any questions on that there? At this point, to find the delta H of that reaction, we're going to use all of our adjusted and correct values for delta H's, which in this case would be, I believe, that number, and that number there. So we're going to add all 3 of those numbers together. That gives us minus 393.5 plus minus 592.2 plus a 1072. Gives us an 86.3 kilojoules in this case. And that means that this reaction is again going to be endothermic, right? And positive value. Any questions on Hess's law and how to kind of do it there? So again, like I said, people sometimes get a little freaked out when they have these things because there's a bunch of equations and stuff like that. So the best piece of advice, like I said, is just kind of keep it simple, kind of go one by one, get everybody on the right side, and hopefully everything should fall into place. Any questions on any of that there? All right. So a couple of finishing topics here. Heat and obviously design is of energy, as we talked about, due to that temperature difference, again, always flowing from hot to cold. The change in the internal energy of the system, delta E, is basically the heat, which is like Q that we've been calculating of the system, plus the work. Work could be positive or negative. The work could either be done on something or work can be done on the system. By convention, again, it could either be positive or negative, and that'll give you the change in the energy there by really just adding those 2 values together. Another sort of important sort of thermodynamic property is one that's known as entropy. Entropy is abbreviated with a delta S. Entropy is the amount of disorder and craziness there is in the universe. And the more disorder, randomness that you have, the higher the entropy is. That's the second law of thermodynamics, basically. The way we can see it a lot of times really easily is to look at what happens when we change states. So when something goes from solid to liquid to gas, is the amount of disorder increasing or decreasing? Are things getting more disordered as you go from solid to liquid to gas, or less? They are getting more disordered, right? You're solid, everybody's locked together. Liquid, everybody's moving around a little bit. Gas, everybody's flying around crazy, right? So there's a lot more disorder happening. So in this process, as we go from solid to liquid to gas, the entropy is actually increasing. Which in the case of entropy actually means that it's becoming a more positive value in terms of entropy. And opposite would be true if we went the opposite way, went from gas, say, to liquid to solid, things flying around, a lot of disorder, then goes to liquid where it's not flying around, to solid where it's really not moving all that much. We're increasing the amount of order, decreasing the disorder. So as we go that way, the entropy is actually decreasing and actually will become a more negative number. And when you take Chem 1B, you'll learn all about entropy. I don't know why they throw it in this book. Any questions on that there? Okay, so that wraps up pretty much chapter 10, which is again the last material that will be on our exam coming up on Monday, I believe. Chapter 4 here, so clearly this is exam 2 material. What we just finished obviously is through exam 1. We're going to talk about elements, atoms, ions in this chapter. We're going to talk about really the structure of the atom, some important experiments that led us to a better understanding of the atom. But first, we're going to talk a little bit about formulas and compounds. A reminder that a compound is always the combination of two or more atoms together that involve different elements involved. So that's why water is a compound, which is H2O, oxygen. It's really a basic definition of you've got two or more atoms together. They can be, but for it to be a compound, it doesn't. Right. And water always has the same basically ratio of elements in it. So always 2 hydrogens for every 1 oxygen. And when we write a chemical formula, we use these symbols for the elements, and we do use a subscript to indicate how many of each of the atoms are present. So obviously when we write something like H2O, this has 2 hydrogens, and much like a lot of times in chemistry, if nothing is written there, it is assumed to be 1. So in most cases, we don't write 1 a lot in chemistry. If there's nothing there, it is just assumed that basically there is 1 of it present. So here are some examples. Again, H2O has our 2 hydrogens, 1 oxygen, our CO2, carbon dioxide, 1 carbon, 2 oxygens, 1 nitrogen and ammonia, and 3 hydrogens. We do sometimes come across formulas like something like this, which is calcium nitrate. This has 1 calcium ion, or 1 calcium. The nitrogen here basically is 1, but we do have parentheses, so we do need to multiply it in. So it has 2 nitrogens in this case. And again, the 3, and we need to multiply the 2 into there. It would also have 6 oxygens in this case. So a lot of times we do have formulas that does have parentheses around them, especially with these guys, which are polyatomic ions. We do need to kind of distribute that 2 on the outside into each of the elements that are present there to get the correct number of atoms that there are. Any questions on that there? So if we were to write some formulas here, if we're looking for a molecule that has 6 carbon atoms and 6 hydrogen atoms, we would have C6H6. Again, both of the 6s go, 1 6 goes to the carbon, 1 goes to the hydrogen. We had a compound that had half as many calcium atoms as chlorine. Obviously, if we have just 1 calcium, then we would have 2 chlorine atoms. None of them are negative. That's just from PowerPoint. And a compound contains an equal number of sodium and nitrogen, but 3 times as many oxygens. That's what we got going here. Sodium nitrate, 1 sodium, 1 nitrogen, and 3 oxygen atoms are basically happening there. Any questions on chemical formulas there? So let's talk a little bit about atomic theory. So we're going to talk about sort of the atom and important sort of events that happened along the way. And again, as we go through it, we'll talk about, what you should really know and all those kind of things. So it really all started way back when, and our philosopher there expressed the belief that pretty much everything is composed of these very small, indivisible particles, which he named atomos, which basically means sort of unbreakable, uncuttable. That's sort of a forerunner for atoms as we know it today. And there was a couple of important ideas that happened along the way. It was believed that most substances are mixtures of pure substances, or most materials are mixtures of pure substances. And we talked about mixtures and pure substances. As we talked about, pure substances could either be an element, like you just have iron metal by itself, or it could be a compound, like you got water, H2O happening there. There are pure substances. The law of composition means that a compound is basically always composed of the same sort of composition of each element by mass. So when you have H2O, which is water, basically oxygen has a mass of 16 grams and hydrogen has a mass of 1 gram. So you basically have, for every 1 gram of hydrogen, 8 grams of oxygen that basically comes every time you have water together, right? 2 hydrogens would give you then double the amount of oxygen, which would give you 16 grams of oxygen that occurs in that case. So one of the first sort of important theories about atoms did come from a guy by the name of Dalton. He was an interesting guy, wasn't a good public speaker and stuff like that. He kept weather reports most of his life. So he would wake up and write down the weather every day. He never got married, surprisingly. And most importantly, and the most important thing you could ever learn is he did like to go bowling on Thursdays, right? And that will be on the exam, so don't miss it. Don't say like Friday. Don't say Saturday. Discount Tuesday is not the right day. It is Thursday. So he went bowling on Thursday, and when he had some other things to do besides bowling, is he actually came up with a precise definition of what we call atoms, sort of a theory. Remember that a theory is something, as I already pre-circled, so that was good. A theory is something that can be sort of revised over the years. And it did happen with Dalton's atomic theory. Not all parts of it is sort of considered correct still. So let's go over the different parts, which you should know. He said that basically elements are composed of these extremely small particles, which he called atoms. As I pre-circled there in big red there, all atoms of a given element are identical to each other. They have the same size, the same chemical properties. And as from the big circle there, that is one of the parts of Dalton's atomic theory, which is really not correct. The existence of isotopes basically made that incorrect. An isotope, as we'll talk about, is really the same element, but they have different masses. So clearly, if they have different masses and they're the same element, they're not identical to each other, right? Those two things. The reason they have different masses, as we'll talk about, is they have different numbers of neutrons. So because they have different numbers of neutrons, that also means that those atoms are no longer perfectly identical to each other. He did say that atoms of one element are different than atoms of another, so that is correct. So copper and iron are different. Compounds are composed of atoms of more than one element. So as we've been talking about, that is all good. He also said that basically a chemical reaction only involves really the rearranging of the atoms and recombination of them in a different order. And that really is sort of what happens in a basic chemical reaction. You basically break apart everybody on the reaction. They reassemble on the other side with all the bonds coming together. That is why we balance equations, because of really as well the law of conservation of mass. We don't create nor destroy mass along the way. And what that means is basically if we started a reaction with 4 carbon atoms, we should end up with 4 carbon atoms on the other side. They may be in different sort of compounds and stuff. But because the mass of the 4 carbon atoms we started with is 12 grams each, the mass of the 4 carbon atoms we end up with on the other side, even though they're in different things, will still be about 12 grams each. So we have that conservation of mass along the way. And we really do have the conservation of elements along the way in a chemical reaction. Another sort of aspect that is not sort of considered correctly, which is sometimes attributed to Dalton's atomic theory, is the idea that atoms are sort of indestructible. You don't like ever change an element to something different, stuff like that. And nuclear reactions basically sort of disprove that a little bit. In a nuclear reactions, you have absolutely really no conservation of the elements. You start with one element, you end up with multiple different elements along the way. And basically what happens is we change a lot of the protons and neutrons, which is really the heart of what makes an element an element. It's actually the protons is the important one there. So in like nuclear reactions, we change the protons from one number to another, and that changes the elements, and we actually do sort of change elements from one to next. In basic chemical reactions like we deal with in chemistry, that never happens. We always keep the same number of elements. They never change. That only happens when you get to Chem 1B and you do the nuclear chemistry chapter, then you change the elements. But for everything that we deal with, it's all about electrons, it's all about bonds, it's all about bonds breaking and making. The elements themselves are pretty much conserved all the way through the process. Any questions on that there? So really the sort of 2 things that are not so correct with Dalton's atomic theory is what we just talked about there. And again, the idea of isotopes. So not all atoms of the same element are always identical to each other. This is sort of how he pictured sort of the combination of compounds coming together as collection of different atoms. And each of these cases, they're obviously all nitrogen and oxygen involved, but depending on the numbers of the nitrogens and oxygens are there, depending on how they're bonded together, it will yield some things with obviously different properties, different sort of characteristics. Again, sort of very much like the alphabet where you just have the 26 letters, but putting certain letters together give you certain words that mean different things, right? And it's the same idea here. You could be using the same sort of elements, but how it's put together, the numbers and stuff like that will give you compounds that have very different properties from one another, even though they're technically composed of the same 2 elements, like we see here. Any questions on that there? All right, I think that's a good place to lay it up here for today.